Good afternoon. Welcome to episode number 17 of the ZOOMTOWN experiment. We're moving past a lot of the groundwork or fundamental components of the Zoomy. We've got the sensors pretty well decided, the drive system, etc. So now we need to move on to the next step, which would be getting power to the Zoomy. And that's no easy to do task. Perhaps not as easy as we would like it to be. I have to take into account what I think all the power consumption is, come up with a power source that can deliver power long enough for me to run the experiments, have accessibility to change out the power source, batteries or lithium-ion cells, etc. There's a little bit more that goes into this than just hooking up a battery to the Zoomy. So that's what this episode's about. It's to explain or to talk about how I'm going to power the Zoomy. And then in the next few episodes, we'll go through the subcomponents of that until we have a full power system put in place. So let's take a look at what we're going to cover in this video. We're going to start with a basic premise. I want 4 hours of runtime for the Zoomy. That'll give us plenty of time to perform any experiments and get things reset as things go bad, etc. We have to take into account all of the power consumption for the whole Zoomy, not just the Pico W, not just the motor or the LEDs or the sensor. It's all combined. Cost is critical. This is another high expense item, and it can easily double the cost of the Zoomy, and I don't want to keep running up costs. On a few sensors, luckily, I found lower cost alternatives, but I don't want to be increasing costs. It must be rechargeable. I don't want to be adding to the landfills with wasted batteries every week that we're doing an experiment. And frankly, if I'm using AA's or something like that, I might go through a couple of sets of batteries. I need to be able to deal with multiple voltages in the system. That's going to be a challenge, another challenge in the system. I have to have easy access to the batteries, and it must be compact. It must be compact in order to fit in the size of the space that we have. I can't make the Zoomy too big. The layout's already kind of decided how small it has to be, and I have to work within those parameters. Now let's take a moment to kind of review the power requirements of the system. What I've done, I've come up with a very simple little spreadsheet here. It's not theoretically or technically correct in the mathematics, but it does boil down my power requirements into a very simple, easy way to present it. On the left side, we're talking about all the components. We've got the Pico marker LEDs, which would be the LED on the front and the back of the Zoomy that will kind of communicate status, the motor drive, gear motor, the TCRT 5000 photoreflective sensors, the A3141 Hall effect sensor, the AS5600 encoder module. All of those are pretty well set in stone. I may be adding another sensor here or there, but for right now, these are pretty much what I'm planning on the system. The voltages for each of the devices, we've got 5 volts that'll power the Pico, 5 volts for the LEDs, 3.3 volts for the motor drive, 6 volts for the motor, 5 volts for the photoreflective sensor, 5 volts for the Hall effect, and 3.3 volts for the encoder module. So we've got 3 different voltages we have to address with our power system. Our nominal and peak current requirements, some of these are estimated, some of them are actually practical values where I've connected up the device and measured it under stress, etc. Let's start with our Pico. The Pico actually has an idle current of about 20, but because there's potentially continuous communications via Wi-Fi, we will be between 30 and 40 milliamps for nominal and peak. Even while the Zoomy is parked in a driveway, it still has to communicate. The LEDs will be between or right around 5 milliamps, give or take, up or down. I don't want them real bright, so I might have to dial them down a little bit, but that'll play out in the next phase when we're working in that area of the Zoomy. The gear motor is definitely between 140 per motor, running idle, just moving along. If it's sitting and not moving, it's drawing just about no current. But when it is rotating and there's nothing holding the Zoomy back or causing load on it, it's about 140 milliamps. And then the peak is 430, and that's at a near stall. We really shouldn't be seeing that condition, but I need to account for it. Our photoreflective sensor, we're going to be pulling about 30 milliamps from what my early test said. I thought that seemed a little high, so I'm going to double check that one, but I'd rather estimate high rather than low. Infrared LEDs can be power hogs sometimes. The Hall effect sensor is very low, 3.5 milliamps. There is no peak or nominal load on that. And then the encoder, although I haven't verified that one, should take about 6.5 milliamps. And assuming everything stays as it is, we'll have one Pico, 3 marker LEDs, 1 motor drive, because that serves 2 motors, 2 N20 gear motors, 3 photoreflective sensors, 3 Hall effect sensors, and 2 encoder modules. When we add all this up, we're running between 30 and 40 milliamps for the Pico, 15 milliamps for the marker LEDs, 5 milliamps for the motor drive, and between 280 and 860 milliamps for the motor. That's a big power hog, as you would expect. 90 milliamps for the photoreflective sensors, 10.5 milliamps for the Hall effect, 13 milliamps for the encoder modules. All told, that would be between 440 milliamps to 1,034 milliamps of current or power. I looked up some of the 18650 cell specifications, and we're going to be probably running 2 in series. I'd rather have extra power in reserve rather than not quite enough power to meet my run time. But we will have 2 in series, giving me a nominal voltage of 7.4, and that will have a typical capacity of about 3,000 milliamps per hour. And with that, if we take our milliamp capacity and divide it by what our expected load is, our runtime will be between 6.8 hours and 2.9 hours. It's a little bit, if we're running at full peak all the time, we're going to have other problems. So I think we'll be somewhere in the middle here, probably closer to the 5 or 6 hour or 6 or 7 hour runtime range than we will be to the 2.9. Just because I know the Zoomy will actually be spending more time in the driveway than it will be running around in ZOOMTOWN. So our runtime, based on 18650 cells, looks like it's going to fit the bill really nice, especially having 2 batteries or 2 cells in the car. So I'm really kind of happy with that. As far as these numbers here, again, this is a mixture of theoretical, calculated, and practical data that I've collected to come up with this amount. Now, if you're wondering why I chose 18650 cells, they hold a tremendous amount of power in a very small and lightweight package. They're very common, easy to get a hold of. There's many sources for them, and we can get chargers for them relatively easily as well. If I went with AA's or AAA batteries, those sorts of batteries, you don't get as much energy density, so you end up with a bulkier package. I've got to have a compact system to fit within our requirements. So now with that, let's take a look at the schematic, and then we'll take a look at the actual hardware that I'm working on. We're going to need a way to hold the two 18650 cells, and I think that's going to be a DIY system. I'm going to make a battery holder, and that's what I'm showing here. We'll be using some PCB with some battery contacts on one end and on the other end. The leads will be soldered on. I don't want connectors where I don't need them. It just adds cost and bulk. And that's what this block area really is going to be, is just the basic battery holder and the battery cells, or I'm sorry, the cells and the cell holder. We come down below to what we call the power distribution deck, and that will be the current or voltage will come in via a pair of screw terminals, and then that will be distributed to each of the individual DC to DC converters. There will be a power switch in here so that we're not powering the system unless the switch is turned on. Getting from the two different DC to DC converters in one area and a DC to DC converter in another area, we'll need a terminal block to allow for wire connection there. I do want a power indicator lamp just to help me keep track of things. If I got to observe anywhere from 15 to 20 zoomies on the track, I want to be able to tell at a glance that the thing has power or doesn't have power to understand what's really going on out on the test track. So on the 5-volt line, we'll put in an LED indicator with a resistor, a current limiting resistor. And then from there, it'll be screw terminals or DuPont connectors taking the voltage and current out to the remote components, such as the Raspberry Pi Pico. This one will be on a distribution area that will help power some of the sensors. And then this one, of course, as it states, it's going down to the motor drive. So that's the whole power system in schematic form. Now we'll take a look at it in the real-life components here. This is our Zoomie without the sensor bracket on there. I didn't want to put that on to clutter the view right now, but the sensor bracket, as you recall, goes around the front, and all the sensors are around there. And of course, a whole bunch of wires coming back toward the rest of this. This is our motor drive, and this is a DC to DC converter. That will power our motors. So that'll be a 6-volt DC to DC converter. And that tucks in nicely there and occupies the space well. Coming backwards through it, this circuit board here will hold 2 more DC to DC converters. One will be 5 volts, one will be 3.3 volts. They'll be switched by a miniature toggle switch, which will be mounted on essentially the top of our battery holder. That'll be the next deck up. And we'll have the indicator light and a resistor for current limiting. Again, I'll adjust that to get the brightness I want. And that'll be, the power will be supplied to here through screw terminals. The battery deck, well, here are the cells first. These are 18650 cells. I always mark them in case you might be wondering what's going on here. I got a number 1 and a number 1. I always mark my cells when I'm going to be using them in pairs. So that's a matched set. I will use them from now until forever, essentially, those two cells together, so that I don't end up with an unbalanced load on one cell versus the other. I'm always going to run these in the Zoomie and take them out. Now I might use them in another device, but I'll be using them as a pair. And that seems to just give me a better comfort level that I'm taking good care of my lithium-ion batteries. This will be the deck that will fit over, that'll go this way on standoffs Then the cells, of course, will go in there. On each end of this will be a PCB. Now this one's got a common connector because this is how the battery will make its U-turn when the batteries are connected in series. Over here, this is where the power would come out and feed back over to the board, the main power distribution board. And you'll see that that one's got, the two pads are isolated from one another. This little device here will be used to hold this end plate in place and to contain the 18650 cells in the holder. That is most of the power distribution system and the power system itself. So with that, that'll pretty much wrap up this video just to get you prepared for what we're going to cover in the next few episodes, which will be getting this all built and put together. And I'll show you how I did that, as well as how I make the PCBs for that. And then we'll do the same in the following week for the power distribution panel. And those will be episodes 18 and 19. So I hope you enjoyed this one. I look forward to seeing you in the next one, and thanks for watching.